Finally, we're going to talk about embedding of database tuples directly from the relational database. Okay. Now, uh, earlier ideas of embedding tuples really came directly from uh, text embedding, right? They were inspired by text embedding. They were using text embedding. And so early ideas were things like let's treat the database as a text document, right? Like writing down the tuples. Apply Word2Vec, apply some language model, and use the embeddings that you get on the words as embeddings of the cells, basically. And you can combine them to tuples and so on. And the idea was to use these embeddings to enrich the query language, SQL, with similarity predicates, saying two things are close to each other, right? Using the embeddings. Here's another approach that basically focuses on embedding for tasks, tasks that involve data integration, specifically entity resolution. You have two tables and you want to match between their entities, okay, like people and customers. And schema matching, right? When you have basically two databases with their two schemas, and you want to match between the attributes. This attribute of one should be matched or mapped to the to that attribute of the other. Okay. Now, what is the approach? They have a three-step embedding. They build a graph from a database, not in the usual sense, but I'll explain in the next slide how. They sample random walks from G. Okay, from that they get basically sentences, and then to these sentences they apply Word2Vec, right? Word embedding technique. Now, the interesting thing is that the graph G includes not only tuples, but also cell values and attribute names. We'll see an example in the next slide. And so what you get basically is embedding of tuples or records or facts, embeddings of cell values, and embeddings of attribute names. So embedding of records are used for entity resolution, and embeddings of attributes for schema matching. Okay, so here's an example. You have here five records. So this gives us five nodes, record nodes. We have these cells. Okay, but we look at the values as nodes. Okay, so we don't have, for example, two nodes for a iPad 4, but only one. And so you connect the records to their cell values. And from each cell or cell value, you also connect it to the attributes that include it. Okay, so you can see that this representation is lossy in the sense that you cannot necessarily restore your original database from this graph representation. But as I said, as a result, you get embeddings for records, cell values, and attribute names. Some challenges that they are facing and describing in their work. Well, how do you handle numeric data? Okay, where you basically have a continuous space of numbers. So they bucketize them and get the discrete values. What do you do with the textual data? They have some policy on when to treat the entire text as a single cell value and when to break some text into multiple cell values. Okay. And then missing information, missing values. They also handle that and they use a special null value to represent the non-existing cell value. Okay. Here's another technique from our lab. forward the algorithm, uh, which basically focuses the goal was to look at the embeddings where you can easily, quickly extend them to new incoming tuples without changing the embeddings of previous tuples. Okay. Now, the main idea was that each meta path includes also one attribute from the target relation. And then what it gives you is basically that your random walks select values from this attribute. And then the idea or the intuition is that nodes or tuples that are similar should define similar distributions. Okay, so and that's basically how you want to define your embedding, or that's basically your encoder decoder scheme. Okay, so to be more precise, we use the standard conversion of a database to a heterograph, where tuples become nodes and edges are defined by foreign keys. And then you have not only a meta path, but also an attribute of the target relation, okay? So meta path A is an attribute, is a pair phi A, where phi is a meta path, and A is some attribute of the last relation type, relation name, sigma K, okay? So here are examples. You have here several meta paths. Here you can see the keys and foreign keys that are used for defining these edges. And in the end of each path, you have some attribute from the schema. Gov, indep, capital, name, type, name, and so on. Okay, now they use that work uses a large collection of metapath A's that are predefined. Can be, for example, all of the metapaths or all of the metapath A's that are of length at most 3 or 4. And, um, and then the algorithm uses an encoder scheme that is defined as follows. So if you have a source fact F, okay, for which we want to define an embedding, the metapath A, phi A, defines basically a distribution over the A column in the following sense. You sample a random walk corresponding to phi, okay? Then you get, in the end of it, some fact of the last relation f prime, and where you return the A value of that fact. That's all, okay? So the encoder basically is defined for defines a proximity for every metapath A, pi A, a phi A, sorry, where the proximity between two nodes is the proximity between their phi A distributions, right? Between the distributions that we get over the A attribute. Now, I do not define here what exactly it means, which proximity measure can be used for distribution, but these exist. Okay, now the decoder is basically the usual one, dot product, with some metrics that give some scaling or some coefficients that are specific to phi and A, to the metapath A instance that you are using. Okay, but these ZF1 and ZF2 are common. Okay, so that's how you learn a common representation for all of the metapaths. Now, just a remark that follow-up work basically try to understand what are the good ways of selecting the good metapath. which metapath A's basically give us good embeddings, with the assumption or the understanding that many of these metapath A's are not really useful. Okay, and there was an interesting experimentation where you select a subset of the metapath A's by some strategy, and several strategies are studies in that work. You learn an embedding, you train on a downstream task with these embeddings, and after each epoch, you record both the time of the epoch and the accuracy. So what you get in the end are different examples like that. Every line or every color uses a different percentage of the original metapath A's. And you can see that, for example, this strategy, say, look at so the gray part is what we get by using all of the metapath A's, and the red is what you get by using 20%. So with 20%, you learn much faster, um, and you even in the end get to better results. Okay, and that's all. And it's time to take the takeaways from the whole module three, where we talked about embedding of structured data, node embeddings, and tuple embeddings. Okay, so uh, in embedding in structured data, our goal is to learn or come up with a vector representation of each item to reflect its semantics. And its semantics is given by the data, is defined by the data. Okay? And the principle is that elements that are nearby, items that are nearby, should have similar or nearby vectors, embeddings, and vice versa. Okay? If two elements are similar, then their vectors should be close to each other. Okay? Now, in node embedding, this approach is basically instantiated or manifested in different cases or instantiations of encoder decoders. Okay? And again, the idea is that you can recover the distance between the elements, some predefined distance, by some simple decoding over the embeddings, which we look at as the encodings. Okay. Now, for defining these proximities or this distance, we use random walks. Okay, and we use different probabilistic functions. Okay, and the the embeddings that we use are basically aiming to learn this probabilistic function with parameters, which include the embeddings. And we also looked at techniques that involve linear algebra, matrix decomposition. Okay, so these ideas of distance between nodes, random walks, probabilistic functions, usually capturing the random walks, and matrix decomposition are generic techniques for producing embeddings of nodes. Okay. Now, when you go to relational databases, you can either use the graph techniques or you use adaptation of these graph techniques to heterographs. Okay, and the ways to enrich them with this concept of metapath. We talked about some reductions to text embedding. And we also saw some specialized instantiation of the encoder-decoder schemes, specialized to databases. And that's all. That's the end of module 3.